Odd song.
A solid uniform cone. So one of these is solid, and the other one is a uniform conical shell. So that's the solid one, that's empty. The two shapes are joined together so the circumference of their circular bases coincide. That's exciting. Find the distance and the centre of mass of the shape from the common circular base. Okay. First thing to stress here is that it's from the common circular base. So we are treating, with two things that we know here actually. We know that because these the cones have the same radius, the centre of mass will lie on that horizontal line through the points. So that's easy, so we don't need to worry about the centre of mass on that direction. What we do need to worry about is the X kind of point where it is. And, well, because you normally think in terms of left to right, even though I thought it's probably going to be on that side, I decided to do what you might normally expect to do and take that as being my positive point there from the centre, because they did ask us how far from the centre it is. So having set it up this way, I'm anticipating I will get a negative answer, and I'm expecting my negative answer to be considerably less than 8. If it's more than 8, I know I've got serious problems. If it's positive, I'll be a little bit surprised, but I can probably live with it. So, one of the things that we've done lots of times with this is we've set it up with a little table. And it doesn't matter exactly the details of your table, but what I've got is a solid cone, I've got an empty cone, a shell, and I've got my total. And I want to think about some of the things that are happening with this. The mass is fairly easy, double S. The solid cone, I'm told, has mass 4. It says that in the question. The shell has mass 0.4. So using my amazing powers of mathematical addition, I feel that the total is probably 4.4 kilograms. Now I'm going to think about where my centre is. Again, we're already open on this page, aren't we? It's alright, it's okay, the video won't mind having brains and walk in front of it. Right, we are on the same page in the formula booklet, at which point we already have a hemispherical, where are we? A solid cone of height h, it's 1/4 of h above the base. Remember? So 1/4 of h above the base. If we're going to put the x coordinate of this, we want to go 1/4 h above the base. Well, h is 8, so 1/4 of that is going to be 1/4 of 8. But that's in the negative direction, isn't it? So that's minus 1/4 of 8 in terms of what I'm doing. The next thing on here says a conical shell. It's 1/3 of h. So the other one is 1/3 of h. And that's to the positive side of my line that I'm working with. And this is what I'm after, is x bar. And so for setting up the table, you get some credit just for doing that. Now we do our moments thing, where we take moments about that centre point, and we say we would have 4 times minus 1/4 of 8. I could really have just written minus 2 there. Plus 0.4 times 1/3 of our 10 is 4.4 times x bar. That's too easy like that, doesn't it? And if we rearrange that, we get x bar. This comes out being just negative, divided by 4.4, we get minus 1.52, or 50 over 33, exactly. Now, the question said, find the distance of the centre of mass of the shape from the common circular base. So the distance that we're after is 1.52 centimetres. Okay, and if we want to be exact, we could say it's 1.52 in the direction of the solid cone. But they just wanted the distance, they didn't need any more than that. Great. Next, we are told that it is suspended from strings attached to the vertices of each cone the object is in equilibrium with the strings vertical and the axis of symmetry about the horizontal diagram. So actually now we're looking at the diagram, aren't we? This is what the diagram is showing us with the strings attached. Now I felt I didn't really have a need to draw the whole thing again. So I said, here is I called the two ends A and B, perhaps sensibly. I said the tension in A is tension with a little subscript A, and there's the tension at B. This line is the centre line through the 2 points that goes right through the middle. Here is a distance 8 and 10, and I'm going to show the weight of the whole shape, which acts. Well, I could have actually just dealt with the two separate ones and kept, lacked confidence in my initial part one and put the two of them on and done it with all of the terms. But actually, I felt confident I'd done the first bit right, so I put in my 4.4g there, and that distance there is about 1.52. And now we've just got to deal with this situation here, work out what the forces are. I've got two unknowns, but if I take moments about any of the points, let's take moments about A, then I would have, this distance times 4.4. That distance is 1.52 less than 8. So that is 4.4g times 8 minus 1.52. Is equal to, that would have a moment in that direction, this would have a moment in the other direction, and that is 18 away, so that's TB times 18. There's an equation that we can solve, and it gives us that the tension at point B is 15.5 newtons to three significant figures. I now need to find the tension at A. I've got choices now. I could take moments about B and do the same method again and get it that way. Or I could use the fact that if I resolve vertically, then I've got equilibrium, so I've got TA plus 15.5 is 4.4g. Which gives me, if I rearrange that, 27.6 newtons. At the end of that, taking 15.5 away from 4.4 times 9.8. And there we go. Again, we came unstuck a little bit from that thing of reading the question. And you've got to try and keep things as simple as you can. So this wasn't really about the cones, this was about that line and the forces that acted on that line. In fact, there are only three of them. Keep it simple. And there we go. Right. Thanks, Johnny.